Welcome everybody to tonight's presentation. I'm going to be discussing EMPs and coronal mass ejections and protection from them. It's a subject that is widely misunderstood, and so I hope to shed some light on that. So first of all, let's discuss what an electromagnetic pulse is. An EMP is an electromagnetic pulse caused by a detonated nuclear weapon. That's why the nukes were going off in the background. A HEMP is similar, but the device is detonated at high altitude, anywhere from 50 miles to 300 miles above the surface of the Earth. And it is known as a high altitude electromagnetic pulse. There are three parts to an EMP pulse. They're referred to as waves, the E1 wave, the E2 wave, and the E3 wave. Wave and pulse are used interchangeably. Now, we're going to compare that with the coronal mass ejection because they are similar with one of the waves that they produce. A coronal mass ejection is a huge amount of released plasma and the accompanying magnetic field from the solar corona, from the sun itself. They often follow solar flares and are normally present during a solar prominence eruption. The plasma is then released into the solar wind, and if it's directed towards Earth and the Earth receives it, it produces E3 types of waves. And don't worry, we're going to discuss what all that means. Here's a picture of a coronal mass ejection that's going on. Fortunately, it's shooting off to the left of us. We like those type of CMEs. And here is a actual, well, let me go here. Here's an actual video of the CME of the sun giving off a coronal mass ejection. It is sending billions of tons of particles out into space, and so long as it doesn't hit Earth, we're okay. So, what's the difference between an EMP or electromagnetic pulse and a coronal mass ejection? Well, very simple. Both types of events produce electromagnetic waves, but only an EMP and consequently a high altitude EMP, they produce the E1 and E2 waves. Both EMPs and CMEs produce E3 waves. So that is the common wave type between both of them. So that's why we're talking about them, because the E3 wave can cause havoc. As a matter of fact, both types of events can bring the electrical grid completely down, possibly requiring years to rebuild. So we've talked about the E1, E2, and E3 waves. What are they exactly? Well, we're going to discuss that. I'm going to show a graph that shows the three different parts of an EMP pulse and consequently an HEMP. You'll notice that the HEMP waves are shown on a double logarithmic scale, and I'm going to explain what that is. That it shows both induced voltage amplitude per meter versus time in seconds. And I'm going to turn on my laser pointer. So a logarithmic scale is a scale that is not linear. In other words, most meters, as a matter of fact, are logarithmic scales on your ham radio, SWR meters. And we can see that on the volts per meter, it is a logarithmic scale as well as the time. So that's why it's this is on a double logarithmic scale. The E1 pulse is shown right here. Look at the amount of voltage, volts per meter on an E1 versus the time. So 10 to the negative 7, 10 to the negative 9, 10 to the negative 11. A 10 to the negative 11 second is 1/100 billionth of a second. So it's extremely fast. And we're going to talk about all that as we go on here. So let's talk about the E1 pulse, which, by the way, is the most destructive part of an EMP. The E1 pulse is known as the early time E1 wave. And that is the thing that destroys electrical transmission lines, transformers, electronic and electrical equipment, whether or not it's connected to the grid. It makes no difference. You can have your ham radio unplugged, and if an EMP affects you, it will fry the electronics inside your ham radio. And again, it does not have to be plugged in. It has the wave shape, and we already saw that as a double exponential with the extremely fast rise time of about 5 nanoseconds. 5 nanoseconds, that is 5 1/1000ths of a second, and a mid-level decay time of 150 nanoseconds. Extremely fast. It can induce up to 50,000 volts per meter on electrically conductive material at ground level. Now, here's not to add insult to injury, but there's a horrible truth, and that is there are countries that are capable of making EMP-focused nuclear bombs that are able to induce up to 200,000 volts per meter on electrically conductive objects. You'll see that 200,000 volts per meter a couple times, but we're going to, this presentation is based on 50,000 volts per meter, which is what a normal EMP would produce. But this was nuclear explosions back in the 70s, okay? We've gone way past that. So we talked about the E1, the most destructive, 50,000 volts per meter. The E2 pulse is called the intermediate time, and it overlaps the E1 curve and resembles a lightning strike lasting about 1 or 2 seconds. It can induce about 100 volts per meter in conductive material, assuming that we're dealing with a 50,000 volt per meter EMP yield. And then you have the E3 pulse. The E3, or the late time wave, resembles an energy surge lasting several minutes. This surge will affect electrical equipment if it is connected to the grid. And by the way, the E3 pulse is the thing that is common between a coronal mass ejection and a high-yield nuclear bomb that explodes high up in the atmosphere. So again, talking about the fast rise time of the E1 pulse and why it is so destructive. The physical length, the electrical conductivity of the equipment, and the fast rise time of the E1 pulse is the thing that determines the voltage level that is induced into the equipment. So we're going to talk about why your equipment is fried so quickly. So as an example, if you take a simple 6-foot-long electrical cord that's may or may not be plugged into the outlet, I don't care, but just a simple 6-foot electrical cord that can receive up to 100,000 volts by the E1 pulse, okay? And it doesn't even have to be plugged into anything. A 4-inch cell phone could receive as much as a 5,000 volt pulse, which of course would instantly fry the cell phone. We're not talking a slow burn, you know, a slow fuse, a slow burn fuse. We're talking instantaneous vaporization of the components inside of the phone. So back to CMEs. When's the last time we had a significant CME? Well, we did have one. The largest recorded geomagnetic perturbation resulting presumably from a CME. We think that's what happened. That hit the Earth's magnetosphere was the solar storm of 1859, known as the Carrington effect, which took down parts of the recently created U.S. telegraph network. It started fires and even shocked a number of telegraph operators. Some telegraph operators, on the other hand, were able to continue operating with their batteries disconnected, powered only by the aurora-induced currents in the lines, with normal or even improved signal quality. A pair of operators, as a matter of fact, in Portland, Maine and Boston, Massachusetts, they were talking for nearly 2 hours without any man-made power supply hooked up to them, and they were talking like they were next door. Now, the EMP is really a cause for alarm. Life as we know it in America would end in seconds if an enemy were to launch and detonate a nuclear weapon high over the center of our country. It is estimated that a successful high-level electromagnetic pulse could be hundreds of thousand times more devastating than the 9/11 attack and could literally decimate America. It would fry the nation's electrical grid and the circuitry that powers our homes, businesses, hospitals, phones, cars, planes, traffic lights, ATMs, water supplies, pumps, and anything else that's not hardened against such attacks. Dr. William Graham, chairman of the Commission to Assess the Threat to the United States from Electromagnetic Pulse Attack, testified to Congress that within a year after an attack, nearly 2/3 to 90% of all Americans would be dead from starvation, disease, or from freezing to death. Following an event of this type, life could become even more difficult for us than it was for those living in the 1800s. And I bet you can guess why. During that time, most people lived on or near farms. They had horses for working their farms to produce their own food and provide transportation. They had their own water and fuel sources nearby, made their own clothing, and were generally independent and self-sufficient. Today, we have a population tens of times larger, which cannot be sustained without electricity and municipal services. Most now live in cities many miles from food, water, and fuel sources. Our computers and microchip controls our vehicles, trains, and airplanes, most of which would become inoperable. Much of our food, at least 35% of it, is imported. Nearly all is shipped from long distances. Today, only about 2% of the US population is producing food, but nearly all of these depend on large farm transport and processing equipment requiring electricity, or on fuel, which must be pumped by electricity. Even if some food could be produced, most of it would perish since it could not be dried, refrigerated, processed, or transported to your local grocery store. Without electricity, nobody could go to work. Manufacturing plants and businesses would be closed. The stock market and bank transactions and records could be lost, since all this information, as well as backup copies, are stored electronically. And I want you to have a good night's sleep after that little piece of news. There are literally thousands of transformers in the power grid, with about 300 of them being considered hypercritical. Most of these hypercritical ones have no spare or backup parts. They are not even manufactured in the US, and some have an order wait time from 1 to 3 years. Also, our civilization has become very interdependent. In order to make repairs on the power grid, for example, there is a need for telecommunications, but telecommunications requires the power grid to work. Whoop, I missed a click there. Even the financial network must operate to maintain the economy. We need the transportation system, roads, streetlights, and control systems to operate just to get people to the filled power, telecommunication, and other systems. Without the existing infrastructure, the military would also have some issues. So we rely on outside sources for our inside infrastructure. And I want to know who thought that was a good idea. Just saying. So why is the E1 pulse so devastating? Well, it is fast, extremely fast. The E1 pulse starts at about 1/1,000,000th of a second after detonation. The rise time is only 5/billionths of a second. The E1 pulse is also powerful. The energy induced by the E1 pulse is, again, approximately 50,000 volts per meter, but that is old news. It could be 200,000 volts per meter. This E1 pulse is way too fast for normal commercial transient spike protectors to handle. In other words, you know that $200 power strip that you have all your TVs and stuff plugged into, your computers, maybe your ham radio, won't do it. The E1 component is produced when gamma radiation, and this is kind of the only technical part of the whole spiel here. The E1 component is produced when gamma radiation from the nuclear detonation knocks electrons out of the atoms in the upper atmosphere. These electrons are now traveling close to the speed of light into the lower atmosphere. In the absence of a magnetic field, this produces a large pulse of electric current vertically in the upper atmosphere over the entire affected area. The Earth's magnetic field acts on these electrons to change the direction of the electron flow to a right angle to the geometric field. This interaction of the Earth's magnetic field and the downward electron flow produces a very large but very brief electromagnetic pulse over the affected area. And so let's talk about the affected area. The area of EMP coverage depends, like I said earlier, on the altitude in which the detonation happened. Even though that it's expected that not all EMP strikes will be successful, if there are attempts, we should plan as though they will be. And here's a map of, based on the burst altitude, how much of the US it will affect. So if the burst altitude, if the HEMP were to explode at 30 miles, then the effective radius is almost 1,000 miles across. If it's 120 miles altitude, then we're dealing with almost the entire of the United States. 300 miles is the magic number. 300 miles, it will encompass not only the continental United States, but also much of Canada and Central America, I should say. And that's just the E1 wave. The E2 component, again, is that intermediate time pulse that lasts from about 1 microsecond, that's 1/1,000,000th of a second, to 1 or 2 seconds after the beginning of the electromagnetic pulse. The E2 component of the pulse has many similarities to the electromagnetic pulses produced by lightning. Although, this is the only silver lining on this, the electromagnetic pulse induced by a very close lightning strike may be considerably larger than the E2 component of a nuclear EMP. Because of the similarities to the lightning-caused pulses and the widespread use of lightning protection technology, I mean, we already have that, the E2 pulse is generally considered to be the easiest to protect against. But here's a problem. And we're going to talk about what that problem is in protecting against the E2 wave. According to the United States EMP Commission, the main potential problem with the E2 component is the fact that it immediately follows the E1 component, which will probably have damaged the devices or systems that would normally protect against the E2 wave. So even though you may have a surge suppressor suppression device that will take care of an E2 wave, that will be defeated by the E1 wave that happens before. Now to the E3 wave. The E3 component is very different from the other two major components of the nuclear EMP. The E3 component of the pulse is a very slow pulse, lasting tens to hundreds of seconds, that is caused by the nuclear detonation, heaving the Earth's magnetic field out of the way, followed by the restoration of the magnetic field to its natural place. That is what the E3 wave does. The E3 component has similarities to a geomagnetic storm caused by a very severe solar coronal mass ejection, or CME. Like a geomagnetic storm, E3 can produce geomagnetically induced currents in long electrical conductors, which we have all over the United States, called power lines, which can then damage or destroy components such as the power line transformers. These currents are often called quasi-DC currents because they resemble the direct current from a battery more than what most people think of as a pulse. Nearly all of the damage from E3 in modern systems occurs to the AC power grid, which is generally not designed to handle direct currents. Matter of fact, the AC grid is not designed to handle DC current. It was Thomas Edison who wanted to have the DC current sent to all of our homes, but it was Mr. Tesla who wanted AC current. And because of distances, AC won. AC is much better suited to carry the current long distance, because we, of course, as you know, in order to do that, we use these 175,000 or plus volt high tension lines that comes from the power grid or power stations, travels long distances. The current, however, is much lower, high voltage, low current, until it gets into the little transformer on the power pole where your home is, that takes the 3,000 volt down to 120 volts. You get two legs of 120 volts producing 240 volts. So it is because the AC grid is not designed to handle DC current. There's where a lot of destruction happens, because the AC infrastructure is having to battle the DC currents. So the big question is, how do you protect yourself against an HEMP or a CME? You can't. Well, actually, I'm kidding. The ideal solution would be to have the entire house shielded, but the cost of doing this would be as much as the cost of the home itself. So for this reason, the goal must be to identify and shield all critical pieces of equipment that are considered essential for one's survival following an EMP strike. People may be on life support systems or something of less life support, if you will, oxygen concentrators. There's a host of things where the medical you have medical equipment inside your home. That's the stuff that needs to be watched out for. Ideally, these critical items must remain operable no matter how intense the EMP signal is, because remember, we're not talking just about 50,000 volts per meter EMP yields, but we're also talking 200,000 volts per meter EMP yields. So critical items must remain operable no matter how intense the EMP signal is, and no matter when it occurs. It could happen at 3 in the morning. It could happen at 3 in the afternoon, whenever the bad guys decide to do it. The list of critical equipment will be different for each family, but would include things that that would include electronic equipment containing microchips, equipment containing discrete electronic components, and equipment containing electric motors. Those are the three types of electric entities that you'd have to watch out for. Much of the equipment not on the survival critical list will be sacrificed, and this includes large items like refrigerators, freezers, furnaces, room heaters, fireplaces, air conditioners, ceiling fans, large TVs. I think you get the idea. Anything with that is using the electrical grid could be destroyed, and quite possibly vehicles. Older vehicles, not so much. Newer vehicles. I'm going to pick on Tesla. The Tesla vehicles, all electric. All they will be is just a brick in the road. To avoid destruction of one's electronic equipment due to an EMP strike requires equipment to be stored within protective shields or containers referred to as Faraday cages. You've probably heard of Faraday cages before. These shields or Faraday cages, and this is the trick, must suppress the strength of the EMP pulse down to a level that the equipment can tolerate. This, if you forget about everything else tonight, remember this. In order for a Faraday cage to work, it must suppress the strength of the EMP pulse, and I'm talking about all three pulses, especially the E1 pulse, down to a level that the equipment can tolerate. So for the E1 pulse, the fast rise time, you must take into consideration the quickness of it, the fast time of the pulse, the physical length, and the electrical conductivity of the equipment to determine the voltage level that could be induced into the equipment. All three of these things are used in the equation. As an example, and I already talked about a 6-foot long electrical cord, it could receive up to 100,000 volts if it's not protected. A 4-inch cell phone, unprotected, could receive a 5,000 volt pulse. This E1 pulse is way too fast for normal commercial transient spike protectors to handle, because, as I said before, it needs to handle a 5 nanosecond response time. And I will say that there are things now that are arriving on the market that's supposed to handle your whole house. I have some questions about that, but that's another presentation later on. The E2 pulse, as mentioned earlier, overlaps the E1 and resembles the lightning strike. It can induce approximately 100 volts per meter. And although the E2 pulse is easy to protect against, remember, it follows the E1 pulse, which more than likely will have defeated the safeguards and protection for the E2 pulse. And then you have the E3 pulse, the late wave, which resembles an energy surge. Very simple to protect against that. If it's connected to the power grid, what do? Well, you just unplug it. The E3 pulse is the kind of pulse, like I said, that is produced by a CME. And unplugging the device from the power grid and reducing anything that can act as an antenna is usually enough to protect the devices. And this only holds true if we're just talking about a CME event. If we're talking about an EMP, the E1 pulse has already destroyed it, so it doesn't matter. So it's probably already toast in an EMP event. So how much is enough? This is the important part. The amount of suppression of a signal is usually expressed in decibels, and you can calculate that with an equation, and I have the equation there. The amplitude ratio is the amount of signal attenuated by the container. So we have a container, and we need to know what the amplitude ratio is. Again, if the EMP is 50,000 volts per meter, and we want the container to reduce it inside of the container to 5 volts per meter, then the amplitude ratio would be 10,000. That's 50,000 divided by 5. And so you plug that into the equation, log of 10,000 is 80 dB. As a matter of fact, the 80 decibel is the military standard for EMP shielding. Again, this is assuming that we're dealing with 50,000 volts per meter EMP. So here is a diagram of the decibels. There's the 80. That's our goal. We want to reduce things down to 5 volts per meter. So the amplitude ratio is 10,000. That 5 volts per meter equates to 1.5. So just a little more than a AA battery volts per foot, or just a very small fraction volts per inch. That is the goal. That is what we're looking for. And I give a couple examples here, a 4-inch cell phone. If the container were to be a 30 dB worth of shielding effectiveness, then that cell phone would receive 160 volts, which of course would fry it, because the phones are good, the components are good to about 10 volts, so you would have a problem, right? Example 2, we have a 1-foot power drill with the power cord wrapped around it. It's placed in the same container. That's a 30 dB attenuation. It would receive a pulse equal to about 482 volts, which is 482 volts per foot times one foot long. And this item would probably survive the voltage level depending on the nature of the equipment. So a power hand drill might do that. But if you take that same power drill with a 7-foot cord, and it was not wrapped around the drill, using a 30 decibel attenuation container, the induced voltage would be almost 4,000 volts, and of course it would fry the motor coils. There would be arcing, and the drill would be inoperable. And the last example, if you put that same drill with the cord wrapped around it, and you put it in a 55-gallon barrel with a 76 decibel suppression, the drill would see a pulse of around 1.5 volts to 5 volts, well within the insulation ratings and below the 120 volt operating voltage of the drill. And so consequently, it would survive. So the size, type of equipment, and container suppression levels matter. That's the magic trio right there. All 3 parameters must be taken into account to ensure the protection of the equipment. Now, this is something that's very good, and this works to our benefit. If you have an object and it's placed in multiple containers, then the resulting protection will be the sum of the suppression of each container. So if I take that same 30 decibel suppression level, and I have another container with 30 decibel, and they are housed in one another, my device would enjoy a suppression level of 60 decibels, which is a lot better than 30. Again, this is, of course, it is 2,000 volts per meter, and several of our enemies have announced super EMPs capable of producing 200,000 volts per meter. So you need to adjust the numbers there. The secure position is to choose a combination of containers which yield the highest suppression possible for the size and type of equipment you are protecting. And this makes it very difficult to protect ham radios, because what do? We have those ham radios in our ham shack. And if our ham shack is not EMP protected, which unless you spent hundreds of thousands of dollars just for the EMP protection, all of your equipment is fried. End of story. So do you buy another ham radio and put it in an EMP Faraday cage? That's a question only you can answer. I was going to talk about how electromagnetic shields work. It's worth going over. I'm just going to highlight a couple of things. This is really a 2-hour presentation, but I'm going to start cutting things out. So I will say that the whole issue with shielding comes down to the size of the hole, and that pun intended. So you want to make sure that your shielding has very few, if any, holes. An example, a 1 mil thick aluminum foil can provide 94 decibel suppression, providing there are no holes in the aluminum foil. Also, this 1 mil thick, I highlighted the 1 mil because the thickness of the container also matters. The heavier the gauge, the material, the much better it is to keep the induced voltage on the outside skin of the container. The amount of leakage of energy into the container is determined by the signal wavelength and the size of the holes. And I'm going to show an example here using a microwave oven. If you look at the glass door of a microwave oven, you see a lot of teeny holes. How many people have ever wondered why you're not getting zapped when you're watching your food getting zapped? The reason is the size of the holes. So the holes are about 1.2 millimeters, and there's about 50 holes per square inch. The table that I'm going to show next describes why we can see our food cook without our face getting cooked. So the microwave oven, the frequency of microwaves is 2.45 gigahertz. The wavelength is 122 millimeters or 4.8 inches. The ratio of the wavelength to the hole size is 100, 10 times 10. So there's a magnitude of 10. Visible light, of course, goes through because the wavelength is 0.38 millimeters. And so we can easily see it. But these other things, these are really large wavelengths. And we're going to talk about using a microwave as a Faraday cage, because people seem to think that works. So back to what I'm talking about here. The table that I just showed you, you can use to determine the signal suppression of a Faraday cage. Again, you're looking for the effective frequency and wavelength and the size and quantity of the holes which allow leakage. So it's those things that determine the usefulness of a Faraday cage. The military has defined the minimal dB shielding required at different frequencies, and here is the mil spec for that. You can see that the 80 decibel is their requirement, and a lot of different things that you can see here along the side give you the relative shielding effectiveness on this scale here versus the frequency that you're trying to protect. And I might make mention that EMPs, they deal with not only the frequency of a microwave, which is 2.4 gigahertz, but all the way down to 100 kilohertz, all the way up to 5 gigahertz. That's called DC to daylight, if you've heard of that before, which again is a frequency range from about 100 kilohertz to 2.4 gigahertz, and some people say it's 5 gigahertz. The point is, a Faraday cage needs to handle the frequency range from way down here all the way up to here. This is why microwaves don't do the job. And we're going to talk about that a little bit later on. So here's a warning that I want everybody to remember. Several persons have posted videos on the internet demonstrating that their metal garbage can, when used as Faraday cages, will be good as a Faraday cage. They put their AM or FM radio in the metal garbage can. They close the tight lid, and I put that in double quotes because there's numerous holes that I see in all of these YouTube videos. And of course, the radio stops playing. But what are they doing? Let me go back up to this here. They are dealing with frequencies that are just a very small range of the entire EMP frequency range. So that's the warning. They conclude that they've demonstrated that their metal garbage can is a good Faraday cage for EMPs. Not so. Their garbage can will be worthless in protecting against the higher EMP frequencies, particularly in the range of 10 megahertz to over in the gigahertz range. And as a result, the contents inside the garbage can will be fried by any typical EMP. There is good news to that, however. Their devices will already be in the garbage can. So there you go. Also, another thing, and I'm going to skip around a little bit, insulation is required. If we use an EMP that can induce 50,000 volt per meter on the walls of the container, you have an 80 dB shielding. Let's say you have a very good container with 80 dB shielding. The inside would remain at 5 volts per meter. That's our goal. There's a 45,000 volt per meter difference between the two. 50,000 and 5,000 or 5 volts. That's 45,000. Typically, a difference of 10 to 30,000 volts can arc across a 1-inch air gap, depending on air pressure, particulate content, and humidity. Also, a difference of 3,000 volts can arc between two items when separated by only just less than a 1/4 inch or 5 millimeters. How thick is a cardboard, a piece of cardboard? Well, it's less than a 1/4 of an inch, but that is what people show that they line their cans with cardboard because they know that insulation is required, but they do not understand. Also, the internal contents must be surrounded by anti-static or other very high resistant material, preventing arcing between them and the container wall. Now, the lid doesn't need to be insulated, providing that you have at least 2 inches of space from the bottom of the lid to your devices. If the container is filled to the top, then the metal lid must also be isolated from the contents. You can buy some really good quality 15 to 24 mil material, polyethylene, having high resistance, 10 to the 11th ohms per square meter, I believe, meeting mil spec, and you can get that on internet on Amazon or eBay. Which brings us to warning number 2. Nearly all Faraday cage articles on the internet indicate that insulation between the container wall is necessary, but they use a cardboard or some flimsy piece of material for that insulation. That will not work. You will get arcing. You're trying to prevent, you got 50,000 volts per meter on the outside of the can. You do not want that to go inside or arc inside of the container. And so you have to have a physical space between the two, plus the addition of very good anti-static bags. So, boy, we can go on here. I'm just going to continue on. I think what I'm going to do is open it up for question, because we've gone 45 minutes and you're going to be able to get all of the information contained in this presentation on the RATPAC website. And so again, as you watch for this, you can pause it and read it yourself. There's one other thing I wanted to go by, and I was looking for this right here. Also on the internet and a bunch of places, it says to ground the containers to earth ground, but you do not want to do that because the grounding will appear as an antenna to the EMP pulse, bringing additional unwanted voltage into the container. So, you notice the airplanes aren't grounded and they get struck by lightning all the time. You do not need to ground it. The only time you want to use a ground for the container is after the EMP pulse happens, if that container is completely isolated, if it's sitting on rubber or wood and it has not had a chance to drain, then and only then you want to go ahead and touch that container, not with your hands, because you will get the shock of a lifetime, but to a grounding wire that goes to ground so you can drain the ground off. And so that's the only time where you would want to use a grounding wire to your Faraday cage. Warning number 3 is about solar panels. Some people say that solar panels do not need protection. That's a bunch of hogwash. There's reverse diodes that will be destroyed by the high voltages. You have long cables that connect everything together. That acts as a large antenna, and the controller is full of electronics. The E1 pulse will fry the solar systems. So this next section talks about different things that you can use. And again, I'm just going to quickly go through here just so that it's included in the recording. And people who are watching this on the internet, they're going, what the heck is that guy doing? But there is so much to go through here. I'm going to give you the source of where I got all of my information. And believe me, it was not on YouTube University. The guy who I follow, who I personally worked with, he worked at MIT. He used the MIT labs to do all of this testing. And believe you me, he is a propeller head. So he has done all of this testing. I've seen the results, and it is incredible. You can also measure your own shielding by doing a couple of things here. And again, I'm just going through here because we have run out of time, and I just want to get all of everything into the screen here. Here's the key right here. J.T. Smith. He's the one who did all of this. And I have included building EMP Faraday cages that work. You'll notice as you read this document that was created in 2014 that almost my entire presentation is built around the work that he did at MIT. And so I have done a lot of other research by a host of other sources, and I have yet to see anything that surpasses what Mr. Smith has done. And with that, I'll take questions. Let me go ahead and stop my share.
Barry, let's hit the comments first. You there, Barry?
I'm here.
Go ahead and hit the comments.
Okay. Tom wants to know, do the EMP coaxial protectors offer any effective defense? And if yes, which waves will it protect against?
Okay, the EMP coaxial protectors, that's kind of a misnomer, but they will protect against the E2 pulse. It will not protect against the E1. The E1 is the killer.
Okay. Dave wanted to know about storing radio equipment in metal garbage cans, but I think you put that in the presentation, so we can read that later. It has to be totally sealed. Scott says that metal Zagus containers are mil-spec rated for EMP. Okay.
I'm sorry, what was the question?
He's made a comment that metal Zagus, Z-A-R-G-U-S containers are mil-spec rate for EMP. So maybe you can find some of those. How about tubes versus semiconductor rigs?
Now, one thing that I will say, you can go to Lowe's or Home Depot and buy those metal trash cans. They're tight fitting. The actual gauge is pretty good. You do not want the ones from China that have a very thin cage. You want the ones made in the US because the gauge of material makes a huge difference. And it is almost required that you have to use the good aluminum tape to seal the lid and where the handles. Every time where they put a rivet or a pop rivet or a screw in there, you've created a hole. That is a place for energy to go through. You need to tape that completely up. You can make a relatively good container using a garbage can from Lowe's, but I like to always use a paint can. A paint can, though, a gallon paint cans, they are awesome for small things. But again, you need to remember you need the insulation value as well. You need to have at least a 1-inch space. And I don't care if you use foam to, 1-inch foam or 1.5-inch foam to do everything, to line your containers with. But make sure that along with the foam, you use the heavy gauge anti-static bags to completely encase your devices in. You can definitely make a good EMP Faraday cage doing it that way. You do not have to spend thousands of dollars to do it, in other words.
Okay. How about tube versus semiconductor rigs?
Okay, semiconductors, forget it, they're fried. Tubes, there's less of a chance for the E1 pulse to affect it. So that is one of the main reasons why tube radios are something that everybody looks for, because of it won't affect the EMP. There may be some tubes that will be destroyed, but hopefully you have spares.
Okay. In amateur radio, there's this maximum permissible. What is the effect on humans of the 2 MPEs up to 2 seconds on humans?
Yeah. Nothing. Zero.
Okay.
You have to be within a number of miles of the explosion for the gamma particles to kill you. The thing what happens with the first explosion up at 100 miles up in the air, the whole idea is not to destroy people or property, it's to destroy the electronic equipment, and then the people will die after the fact. So, but you're not going to get radiation poisoning from 150, 300 mile detonation.
Okay. You already answered this. I think that the metal cans need to be grounded. You said no, correct?
No, do not. The only time you want to ground it is after the EMP, where you could have a surface charge on there. Then I will always touch my grounding rod, my heavy duty cable that goes into the ground to drain off that. It's just like going into the old tube TVs. They have these huge capacitors where we used to put these large screwdrivers to arc it, and you'd have 20,000, 30,000 volts arc going on. The same thing can happen on your trash can that could be charged if it's isolated, which it should be. So yes, do not ground it. You're going to make a bad situation worse.
Okay. Brian posts some guidelines for personal protection in the for anyone.
Yeah, the telecom industry. I'm sorry, go ahead.
Yeah.
I'm just going to say the telecom industry, they have there's a lot of source material for this. I decided to only deal with things that are in my control. I'm not in control of building telecom departments, data centers. They have a whole other source where they get that information. So I decided not to include any of that just because of the time's sake.
Okay.
Can you use a garbage can to fry your eggs? The can does not become heated. Okay. You can get a 50,000 volt. I know it's a joke, but let's be, there's some seriousness behind this. You're more apt to get electrocuted than to fry eggs. Okay. So it will not fry the eggs. So sad. Too bad. Your dad.
That's all the chat.
I'm sorry, you're breaking up pretty good.
Questions from the.
Okay, yeah, I'm reading it now. Will humans know exactly that an EMP event occurred? Absolutely. the first thing that you want to do is look at your watch, your cell phone. If your cell phone is blank and your neighbor's cell phone is blank, and you turn your car over and it's not working, yes, we've had an EMP attack. As a matter of fact, my suggestion is that you read 1 second after. "1 second after" is a book that was written by the foreword by Newt Gingrich, but it was written by William Forstchen. I don't know how to pronounce his name, but it is a story taken from the congressional report that was given to Congress, and in story format, in a fiction format, it describes what will happen to people within the first year of an EMP. So if you want to know the practical sides of survival, I've read this book probably a dozen times, and it goes through, and I've marked all of the things that I've just taught here, and it's all in here. It talks about the practical side, or the real life human side of an EMP event. Good question.
And if you look outside, the cloud, it's too late.
I did not. You're breaking up. Sorry, Barry.
If you look outside and you see cloud, it's too late.
You're really breaking up bad, Barry.
Yeah, I didn't understand anything you said.
Yeah.
Put it in chat.
It's already in chat.
Okay, I see a couple of question, but there's no. Tom, do you want to unmute yourself? Oh, if you look outside, like in my window here, and you see the mushroom cloud, then you're dealing with something a lot worse than an EMP, because now you're dealing with the destructive forces of a nuclear bomb that is at ground level. And by the way, when they do these nukes, they do not do it at ground level. It is up at least 100 feet. And as a matter of fact, the Nagasaki and the Japanese bombs, they detonated something like 3,000 feet above the air, because the purpose was to destroy the infrastructure, not by EMP, but by just the total destructiveness of the bomb. So yeah, you never or below. We did all of our testing. Most of our testing was below ground. Yeah. Pretty. As a matter of fact, I wish I could find the cartoon where, if you can imagine, two men in a fishing boat that have just cast, and they look behind them and they see 3 mushroom clouds with the cities in the background, and the caption on the cartoon was, "Well, I guess there's no limit now," with the fish, right? So I thought that was pretty humorous. Any other questions? It was a lot to go through. I apologize. There really is a lot, but I wanted to make sure that I touched on the majority of things that are miscorrectly identified on YouTube and in the internet. And if you have any questions, please please contact us, and I'll.
My question was, is there a suitcased version of your presentation at full length available anywhere? You had to truncate this because of the time limit.
Right.
Do you have the full length presentation accessible anywhere? Or could you send it to Don for distribution?
Yes. Dan already has that. And so when you go to the RATPAC for past presentations, you'll see some materials to download. there's a PDF of the entire presentation that doesn't go through the, 30 frames a second type of stuff, right? So you can read it at your leisure. As far as an actual presentation, I'm actually going to give it to another club where I have actually 2 hours to do a presentation for, and I can somehow get that to the RATPAC. Again, just doing it in an hour is rough with the amount of stuff that we wanted to cover, right? Because I wanted to cover an EMP and a CME, but now what do you do with it? I wanted to talk about the protection aspect of it. And generally, I give those in 2 presentations, an hour for Faraday cages and an hour for EMP and CMEs. And I had to condense it. So anyway, go to the RATPAC and the core material will be there for sure.
This is a presentation we should have considered doing part A and part B. Carol,
Yeah.
put your hand up. Carolyn,
I thought there was tomorrow night was going to be the second half of this.
would you
Yeah,
not just,
yes,
please not just jump in and raise your hand, please, if you're going to speak.
Carolyn, you have a question, please?
yes. I've heard that you could use a trash can and paint it with lead paint. Does that work?
No.
No?
There's a lot more to it than that.
Okay.
Yeah, the lead paint would have to be very, very thick, and you cannot have any holes. But that's only half of it. You need to make sure that the inside of the container is properly set. You have a good 1 inch, 1.5 inch separation between your equipment and the outside container.
Uh-huh.
I suppose that, see, lead is great for X-ray type of stuff, for the actual gamma stuff. If you had a explosion at ground level, yes, I could see a lead container, but it wouldn't do the devices any good. I would want to be in that container.
Okay.
So yeah, it's not going to do you any good.
Okay, thank you.
Okay, to answer somebody's question about tomorrow's thing, tomorrow's presentation is going on planning and building a wing go kit, nothing to do with what the subject is tonight. We'll have to maybe go back and discuss doing a 2-part on this. This has been a good presentation.
There is a comment in the chat, and I'm glad you brought that up, Paul. Many stories of post-EMP say insulin is no good without refrigeration. So people who require life-saving things need to prepare for this. This is why EMPs are so dramatically horrible, because it will take the sick first. People in the hospital on ventilators, they're gone. And I don't mean to be crude about it, but that's the whole idea behind it. You makes the hospitals ineffective. We're not even sure that most pacemakers will deal with the higher yield EMPs. Okay, so if you have a pacemaker, it's a toss of the coin. This is very serious stuff. So anyway.
Okay, Scott, you got your hand up?
Yeah, I just wanted to let Dan know in Utah, check your email. I sent you a bunch of stuff.
Thank you very much. Appreciate it.
Yep.
Okay, Paul, you got your hand up?
Yeah, I do. I used to have, my late wife used insulin, and I had a dog that used insulin. And I was using insulin also for the dog, whatever was left over at the end of the month, even though that's
your audio's gone.
Yeah, you broke up. Interesting. I've had a dog on insulin, and at the
when
time
she
I
died,
did,
I had a bunch left. He said, look at the insulin, and as long as it's clear, it probably will be pretty good. Like they say, that's what I would do. And if I had an insulin meter that was still working, that would be your backup to do the best job you could with the situation.
Something is better than nothing. Okay.
Right.
So, yep.
Okay.
Tom has a question.
Yes, he does. Go ahead, Tom.
Yes, sir. Are you familiar with gang boxes that are used on job sites to store tools?
Yes.
Would one of those with some of that seal lining stuff, surplus military seal lining stuff work?
Yes. As a matter of fact, the gauge is awesome. But the lid, you need to get rid of all the rubber gasket stuff and put in electrically conductive. They make special gaskets for EMP boxes to replace that, and make sure that any screws, any bolts, any rivets that are there, you have well covered with the appropriate tape. But the other thing is you need to separate your devices from the skin. So in every case, you need to make sure you have at least an inch and a half of space between the skin and the bag that you're going to put all of your devices in. Whether you line it with wood or sheetrock or anything, you want that physical space between the skin and your next material, which is going to be the heavy gauge static bag. And then you put the devices or whatever inside there. Those job boxes are very well suited for that, but you have to do some modifications for that.
You should know that you can buy the edging for openings from any good electrical supply house, although it's likely to be a special order. And it just pushes in a place around a piece of metal. And then when the other piece of metal gets down on it, it's meant to provide the grounding. Remember to remove the paint from above the mating surfaces.
Also, where the lock is, there's a lot of holes in there. So you got to make sure that everything is sealed up. Okay. Which brings me to a question that I'm surprised I have not gotten yet. How about your safe, your gun safe? Excellent EMP cages. If you modify, how the door is closed, make sure you get rid of the gasket. Some safe companies will put a fire type of gasket where in a fire in heavy temperatures, it expands and seals it. That's not going to help you in an EMP. If you want it to be an EMP, you need to pull that fireproofing off and put that, and it looks like a very tight woven material that's metallic, that is squishy, and that's what you put in there for your door seams. So safes can be done, but you have to deal with all the holes.
Okay, Carolyn, you're back to us. Take it away.
Yeah, can you buy those anti-static bags, very large ones that would like go
Yes.
into the only ones I've ever seen are like small ones. Where do you get the real big ones?
eBay is a great source. As a matter of fact, when you go and download the source material that I supplied, open up the document from Mr. Smith, and he describes exactly, even gives you the website on where to get this.
Okay, thank you.
Yeah, you're welcome.
Great presentation.
Who knew?
Yeah, in case anybody wondering, we had this was we had some conflicts and things moving around, and this was a last minute thing. And Dan said, I got this presentation. Wow, let's do that one. So that's that's why it is what it is tonight, and it's great. Dan's doing a great job. However, we should have, if we known then what we know now, we would have looked at doing 2 parts to it.
Yep.
Okay.
We can do another part some other time.
Yeah, we can. We can go through all this and work it out. Okay, I don't know why you're breaking up so bad there, Barry, but you really are.
Okay.
Dennis has got his hand up. Go ahead, Dennis.
Yeah, it occurs to me, nobody's asked this question. And of course, I know the answer to this, but nobody's asked the question. It was kind of surprising. One of the comments you made early on, Dan, and by the way, you did a great job. This is a wonderful presentation. Thank you for doing that. And great last minute, like Dan was talking about from our meeting last night. One of the interesting,
This was a last night decision, wasn't
it
it?
was a last night decision. One of the interesting aspects of EMP is testing. And, you know, early on in your presentation, you talk about the fact that it requires it's a product of a nuclear explosion, but there's other ways to generate EMPs without having a nuclear explosion. And that's how you do the testing, is using high explosives and compression wave, electromagnetic compression wave device. And that's a non-nuclear devices that are actually EMP bombs. And you basically put that near whatever it is that you're trying to test, and you blow it up and see what the results are from the EMP that it generates.
You don't even need, you do not need an explosion. As a matter of fact, the U.S. Army,
it's a shaped charge is what they use to detonate these things. It's a shaped charge that moves a magnet through a coil and induces a current flow. And well, the coil, let's see, you induce a current, let me describe it. You have a coil that you discharge a capacitor through. At the same time, you start a magnet through that coil, and this generates a huge electromagnetic field when you do that. And it's done using high explosives or shaped charge to initiate. Yeah. So those are non-nuclear EMP devices that use testing and what have you.
Well,
yeah, it's a tough business to protect against this stuff, I can assure you.
It's amazing how much we know about something I wish we didn't know anything about for all these reasons. Okay, any more hands that go up there?
Well done, Dan. Thank you.
You're welcome, Dennis.
Yeah, you really came through. This is what, he's had, if he slept last night, he hasn't had very long to work on this. Okay. Any more questions out there in chat or in hands up? Okay, now I'll open it up for comments. Crickets. Be nice.
Yeah, I have a comment. I'm back again. I just looked up large anti-static bags, and they have different types of sealing things, and they've got peanuts. You know those foam peanuts? They have anti-static peanuts. You can put them in the.
That might be good to produce a space between the outside skin and your other bags, but there's way too many air holes. Again, we're dealing with holes. We don't want holes.
Well, why do they have it listed under anti-static?
Well, because they're shipping. This is for sensitive equipment that they do not want static. You know, when you open up a box with a bunch of those peanuts and you stick your arm in there and bring it up and you have an armful of peanuts. That's static electricity. Those peanuts will defeat that. So that is strictly just static electricity. It has nothing to do with the EMPs or CMEs. Yeah.
From Steve Waterman. 4 CJX okay to call.
Okay, Tom, you got your hand up?
Yes, sir. The other things, there are a bunch of other things you can do to take care of not having a lot of electric things in your life suddenly. And you don't need a list from me right now, but if you even think about it, if you're on well water, there are several brands of long throw manual pumps that'll bring enough water to keep yourself away from thirst and stuff like that, that can be put in beside your electric pump. There's a whole list of stuff. So if you look around, you'll find it. There are substitutes for a lot of things. One of the things my Aries group has that we even got a gas station owner to let us try is a 12-volt electric pump that is listed for flammable fuels, emphasis, that will draw the gasoline up out of the underground tank and put it in a vehicle without any other infrastructure. And if that's little puppy, and it is little, is stored away correctly, as Dan has suggested, then out it comes after the problem, and all that fuel stuck underground might be an asset to you. And there's a lot more. Thank you.
Set up your own gas station.
For the cars that are still running, you make a net. Okay, Scott, you got your hand up again.
Yeah. So Dan, so I made a comment in chat about Metals Argus. So Metals Argus containers, the K470 series, are rated from 1 to 18 gigahertz.
What's the attenuation though?
They said that they passed EMI and EMP certification through the mill for mill spec.
Well, okay, so that means that that'll do at least 80 decibels. So that's a good thing.
Yeah, we use a lot of those containers at work to store a
Yeah.
lot of our handheld radios in.
Sure. Send me one of those.
What's the part number again on that?
What's that?
Repeat the part number?
It's part of the K470 series.
Okay, while he's doing that, I might comment on Carolyn's, what Carolyn is seeing on the internet there is they have bags. There's usually two different types of bags for your everyday type of static conditions will wipe out some very sensitive components. And so if you're shipping parts or sometimes a whole device that's sensitive to just your everyday static, rubbing your feet across the floor, that's what those bags are intended for. If you have a big explosion go off, they might not be solid.
Okay.
As a matter of fact, the bags you're looking for, they're very heavy gauge. If you can think of the heaviest gauge freezer bag that you buy in the store with the Ziploc and multiply that by 3 or 4, that is how thick they are. They're kind of a pinkish material. And typically they ship, anything electronic in there. I see them in data centers all the time. They throw them away. So if you know somebody that is building a data center, they may have some extra bags floating around.
There you go.
But
Source.
it's a common thing.
Okay, I don't see any more hands up. And Barry, are you back with us, Barry? He might have been having some problems and left us. I don't see anything more in chat. Do you, Dan?
Let's see. There is a question. Are there any good projects we can build to properly protect our devices like radio-sized ones? Yes, you can do it on the cheap. I use a 50 cal ammo can. I take out the rubber. I put in some metallic foam, if you will, for lack of a better term for it. And I line it with 1 inch of foam. And then I have that pink bag that I put my radios in there. And that's what I store in my safe. So I have a bunch of radios that are stored like that. And the only hard thing was finding the static bags. Once I found the source for that, then I have lots of foam, and you can get the 50 cal ammo cans pretty cheap, right? So you can do things really quick and protect your equipment much better than just leaving it out on your desk.
You want to put the new stuff on your desk so you can have fun with it and put the old stuff in there to back you up.
Exactly.
What would we do for the gun safe kind of thing, or for HF radios?
Like any other container, you need to plug the holes. My gun safe has a big 1 inch screw on top where they actually took it off the truck, right? So that has to be sealed, hermetically sealed. You have to rip off the door liner. Most large safe companies, and I don't know what they might have in the cheaper safes, but I bought a Liberty safe, and it has the fire liner where, again, a high temperature, it expands so that no fire can reach inside of the safe. That has to be pulled off. And you have to put it with that the metallic foam, if you will. and make sure that there's no other places where there's a hole. And with safes, that's the only thing you have to worry about is just the door and the probably the hole where they've transported the safe from. Smaller safes, I don't know. There's probably holes all over the place. There could be some holes underneath, whatever. I'm talking about the larger safes.
To maintain the fire protection of that safe, there are strips that do not have to meet that can be purchased from any fire equipment or fire supply dealer, although they are a special order item. And the reason they're still effective is that when exposed to heat, they'll swell to close the opening, even though they're not in the interface.
Right.
You can
But
put those on after you've put on the interface stuff to protect against EMP. You put that on just outside that.
Nope.
It'll swell shut and protect it from fire.
nope. Well, protect fire, but it won't protect it from EMP.
Oh, but you've done that already. You took the old stuff off, you put the EMP seal on.
No, I'm
No.
saying that if I did it to my safe, I haven't done it to my safe. I have another safe inside my safe that has that I've destroyed. You know, I've voided the warranty. My big safe, I want for fire protection, and you know the skin is actually a 1/4 inch, so it is excellent. I mean, it's a massive safe. That is for burglary and fire. The safe that's inside of there is designed for EMP stuff. Plus, I have my 50 cal cans with some equipment in there, so that's what I use.
I followed you, but you are going to replace the old seal, the fire seal, with the electronic sealing stuff.
Yes,
Right.
yes. If you want it to be an EMP safe,
Yes. So outside of that, it doesn't have to be at all snug. You can put some of this seal that runs around the edge of the door for fire. Okay. You're not affecting your EMP work, but if it's exposed to fire, that tape will swell the opening shut and seal it against fire.
if it's side by side, yes, I can see that. But if it's on top of one another, no.
No,
Side by
not on
side,
top
yes.
at all. Just
Yeah.
it
Okay. Perfect.
doesn't have to seal until it's exposed to heat. So
Right.
it doesn't need to be on top of it.
Yep. Perfect. That'll work.
Okay, Dennis, go ahead.
Yeah, on the subject of safes, I made a comment in the chat, but I'm going to bring it up here that there are a lot of safes out there these days that have electronic locks on them. So you definitely don't want an electronic lock on the safe that you want to protect. You
I
want
have an old-fashioned one.
Old-fashioned S&G lock or something along those lines. Yep, that's exactly what you want. The other thing I was going to comment on, you can get that shielding material that we're talking about, the gasket. It's available on Amazon. I was just looking it up here. I've got lots of it around here because I do a lot of radio work that I do with microwaves, so I use that a lot. But it's Titan RF is the name of the company that makes it. They call it Faraday foam gasket. It's basically a woven gasket with a sponge material inside of it, possibly. Sometimes it's just really springy material like finger stock. And finger stock would work too, but this would be a lot more effective. And it's $30 for a 90-inch piece of that. So that's pretty economical. That would be a good investment. Yeah, that's what you could use. So that's available on Amazon. Oh,
Everything's on Amazon.
good old Amazon. And I was also going to mention, I use a lot of these anti-static bags. This is not one that's going to be very good against an EMP because it has no way to seal it. It's just this would have been, you could use conductive tape on it, but it doesn't effectively seal it. So this was really conductive cushioning is what this was for. So there would have been a circuit board or something inside this bag. And that's all it would have been. But this would not be very effective as a static bag to protect against an EMP because it would be literally transparent. What's that, Dan? I'm sorry.
The bag says do not open, so there's some
Oh yeah, it says do not open. Yeah. Typically, these are sealed with when you get them, they're sealed with a conductive tape. But I wouldn't trust something like this to protect something like an HT or something like that. Or
The only reason why I would use that is if I were to have a radio with a separate battery put in there, tape it so that around all the seams, and put it inside of another container.
put inside
You know,
of the container,
when
yeah.
you start putting them inside of one another, it's an additive property, and what little it adds, it'll add.
Typically, when you like a circuit board in a bag like this, when it arrives, it'll be two layers. There'll be this bag on the outside, which is a physical protection, and then there's an anti-static bag which doesn't have the
Bubbles.
bubble wrap. This has actually got a bubble wrap with anti-static material around it, but then you'll just get the anti-static bag inside this where the circuit board is. So you do have actually double shielding with this, but it's more to protect it physically from damage and shipping is what these are for.
Well, shipping and just handling of the board.
Well, the other bag is for handling the board, and you
Right.
don't want to open one of these just anywhere. You want to do it under proper conditions at an anti-static table.
It says do not open, so we're safe.
And do not, well, there's a caveat. It says do not open except at approved static-free workstations, which is exactly what you do.
That's right.
That's right.
Okay, do we get
Ground
anybody?
yourself.
Any hands up?
Gentlemen, this is Stan. I don't have a hands up button on my phone. I'm sorry. Is this a good time to ask a question?
Go for it.
Great. Number one comment, thank you for putting this on. It was very informative, something that I haven't dove into yet, but I am going to need a new self-help group, because once I bring this up to all my friends, I think I'm going to need new friends. But something I definitely want to read that book. Thank you for sharing that, Dan. 1 second after, I'm definitely going to pick that up. So to my question, as I'm thinking and listening to all that, absorbing everything you guys have put on, is there any kind of proof to having like a bomb shelter type place where if you were going to store supplies, would that be effective in any realm, or would it be just sort of like a grounding? You'd still need to protect everything with the Faraday protection. Thank you.
Yes. And that's another misconception that people have. They'll spend hundreds of thousands of dollars for their bomb shelter, and it will work great for a bomb shelter, but you have to be down hundreds of feet for the EMP to not take effect. And so you need to me, going down a couple dozen feet and with earth on top of you just isn't enough. So it's great for the destructive force of a nuclear threat, but not an EMP threat.
Unless you wrap it to make it a Faraday box.
Yes. And you need to remember that's 50,000 volts per meter. And if you have a container that is 40 feet, you know the type of voltage that will be induced on that container. So you got to be careful. So that stuff, yeah, it becomes very dangerous very quick.
Okay, any questions out there? Comments? We will definitely have to discuss in the board meeting. This has been a very popular one. Lots have gone over time here a little bit, quite a bit.
Sorry.
No, that's okay. It's perfectly fine, especially something like this. We'll have to discuss if we can do a two-part series on this somehow, and so everybody gets all the information. We'll get his presentation out there for those that want to see all the rest of the story, so to speak, and go from there. I'm going to open it one more time, and if I don't hear anybody, see anybody, feel anybody, smell anybody, I'm going to shut this baby down. Okay, it's been a pleasure, everybody. Thank you very much for coming. We'll see you hopefully tomorrow. If not, see you next Wednesday.